Good evening, everyone. I'm Monica von Campania with Education for Tomorrow Alliance, and we are so happy to have you join us this evening for our next distinguished speaker. I think there's some good things to be learned this evening about one way to apply your degree in kind of that research and kind of ongoing teaching. So there's going to be some good lessons for those of you that are starting to begin and explore those types of options. So with that, I want to thank our sponsor this evening, Oventive, who invests deeply in all of our career programs, this being one piece of that. And with that, I will gladly turn it over to our program director, Corinne Coulter, to tell you a little bit more.
Hi, yes, thank you, Monica. I'm Corinne, the program director at EfTA. We're excited to have you guys join us this evening. Just a couple of logistics before we get started. We are in webinar form, so we cannot see you, but you will have a chance. We're going to switch it up a little bit tonight and give you guys a chance to ask questions throughout the entire hour. So if you do have questions, as our presenter is speaking, you can submit them in the chat or the Q&A feature, and we'll monitor those. And then we'll also do a question portion on the back end. So if he's sharing about something and you're like, wait, what is that? I need to learn more, or you have a specific question, type that in. We want to make sure that you are kind of going with the presentation and understanding all of it and its kind of complex of what the work he's doing at Abilene Christian University, which is my alma mater. So we're excited to have you guys here. And I will pass it back over to Monica, who will help us introduce our presenter.
All right. So this evening we have with us Dr. Rusty Towell. He is the founding director of ACU's Nuclear Energy Experimental Testing Lab, which is building the first university advanced reactor in the country. He has a BS in engineering physics from ACU, where he's been a professor for the past 23 years. He earned a PhD in nuclear physics from the University of Texas. He served in the U.S. Navy as an instructor at the Naval Nuclear Power School and completed a postdoctoral research fellowship with Los Alamos National Laboratory, working at Brookhaven National Lab. For the past 30 years, he has worked at many different national labs on several international research projects. He has over 250 articles, some of which I noted were co-written by students, which is something kind of special, and scholarly writings, which have been cited more than 35,000 times by peer-reviewed publications. We are thrilled to have him with us this evening. Dr. Towell, you can take it over.
Thank you so much. I appreciate being with you. It's always exciting to get to talk about things you're passionate about and you enjoy. It's more interesting and even better to talk to people that want to be here. So thank you for joining us on a Thursday evening to talk about something that's really important to me. I've got some slides I think it's helpful. So I'm going to go ahead and share a screen because I think it's more interesting to see slides than it is to look at my face. So hopefully we're able to see the slides. Great.
Looks good.
All right. Very, very briefly, let me just say a few things about myself before we jump into this. And I love the idea of the webinars so that people from all over can join in from their home. What I hate is I can't see you and I can't see whether you're understanding or if I'm speaking to you or above you or beneath you. So please get those questions in because I'd love to speak to you and communicate clearly the excitement of this project and where we're going with it. My name is Rusty Towell. I grew up in Texas. I got my degree from Abilene Christian University, undergraduate degree in engineering physics. After that, I joined the Navy, taught the Navy's nuclear power school. That gave me a real passion for teaching. I really enjoyed that. I already knew I enjoyed doing research because as an undergrad, I got to work at Los Alamos National Lab, and that was really a great experience for me. And so finding an undergraduate degree program where I was actually able to participate in world-class research and solve real-world problems and do it with a mentor that was really working with me and beside me, that's what really shaped me. And that gave me a great foundation. And then when I went to the Navy, I learned I had a passion for teaching. So I went ahead and got my PhD and ended up with my sort of dream job where I could teach and do research. And so over the last bunch of years, I've been doing both of those. For a lot of years, for me to engage students in world-class research, it meant that I had to take them with me to a national lab. So for 20 plus years, I took students to national labs to Los Alamos National Lab, Fermi National Accelerator Laboratory outside Chicago, Brookhaven Lab on Long Island, worked at these different national labs where they have really, truly world-class facilities. The exciting thing that happened is about 5-6 years ago, we took a path at Abilene Christian University where we really started to invest in world-class facilities on campus. And so with sort of the blessing of ACU and our president and board of trustees, we then found an industry sponsor, Natura Resources, to fund that. And we've invested in some amazing facilities on campus, really unique in the world type of facilities to work on a problem that will really change the world. And so pretty big, bold claims, but I hope as I explain this, you'll understand how we're really fulfilling that. So let me jump in and tell you a little bit. First of all, just briefly, I'll introduce Abilene Christian University. We're located in Abilene, Texas, so pretty much center of mass of the state of Texas. ACU's mission is to educate students for Christian service and leadership throughout the world. Our main campus is in Abilene. We're growing. We're growing quantitatively. This school year, the 2023-2024 academic year, marks the 6th consecutive year in a row where ACU has increased our student enrollment. And so we have our largest student enrollment ever, over 6,000 students. But more important than just the numbers, in my opinion, is the quality. And so you have all these rankings by the U.S. News World Report where we've really been ranked high. And it's in no small part to the project that I'm going to be talking to you about. And so let me jump in and tell you what that is. Next Lab stands for Nuclear Energy Experimental Testing, or Next Lab. And what our sort of tagline is, we're trying to find global solutions to world critical needs. If we're in person, I'd ask you to brainstorm what are the critical needs of the world and see if you can sync up with me. But it usually doesn't take very long before we end up sort of coalescing around some of the real fundamental challenges that the world's facing. And so let me just sort of briefly run through some of them. Half of the people will develop cancer during their lifetime. And so there's a lot of different news stories about that, but and I think if you reflect on your own personal life, there's probably not a single person that can't name someone that they love that's meaningful to them that has suffered from cancer. A grandparent, a friend, a colleague. Cancer is something that is widespread. There is some really, really, really promising solutions called targeted alpha therapy, but there's a challenge out there. And I want to talk to you about that. Very briefly, what is targeted alpha therapy? You take an alpha emitter, you attach it to an antibody, it goes into the body, and it kills the cancer cell, one cancer cell at a time, without damaging healthy tissues around it. This case study that I'm showing you is a person that had cancers throughout the body. So black is bad, it's cancer, it's spread throughout the body. PSA levels should be down in the 2 or 3 level. It's up in the hundreds of level. This person was sort of terminally ill, a very short life expectancy, was given some experimental beta therapy, and it continued to spread. So at that point, it became a candidate for this experimental targeted alpha therapy. And after a couple rounds of therapy, PSA levels dropped down to 3. You can see most of the black is gone. And then after a third round of targeted alpha therapy, the PSA levels were below detectable limits. So this person went from being terminally ill to cancer-free with this targeted alpha therapy. And doctors describe this as smart bombs to target cancer cells. And so it's a very, 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 very promising technique. These studies continue to be published in journals and continue receiving awards. But every one of these journal articles will have some line that says, oh, there's just one problem. We have a lack of availability of suitable alpha emitters. And these are radioactive isotopes that decay over time. So you have to harvest them, use them before they decay. You can't store them up. You can't dig them out of the ground. You have to make them, use them, or they will decay away. So that's one of the challenges the world needs is a source of alpha emitters to really treat cancer. Another issue the world has is energy. And so shown in these two pictures on the left, you see what 40% of the world used for energy. It's some sort of wood, biomass, or in the case of this lady here, literally manure, right? You're taking cow pies, working with straw, forming little pies, setting them out in the sun to dry, and then you carry that back into your home and use that animal waste in some sort of a stove to heat your home and cook your food. And you can imagine how those fumes fill the house and cause all sorts of lung cancer and other diseases. And so the world needs energy. They really need inexpensive so that the poorest of the world can get it. They need to be clean so that they don't die of lung disease. They need to be safe, obviously. It needs to be affordable, and available electricity changes people's lives. And I love this graph. When I look at graphs, I always, what's on the x-axis, what's on the horizontal axis, what's on the vertical axis. What's shown on the vertical axis here is the Human Development Index. And so that's how are you doing? What's your standard of living? High on this is what we enjoy in the United States. We have access to good healthcare, education, living standards, et cetera. Low on this is what sort of developing nations are. And what you see, all you need to move from the very bottom to the top, if you now look at the horizontal axis, is how much electricity does each person have? And so if you have zero electricity, your life, your human development index, your standard of living is very, very poor. It's near the bottom. But if you have just a little bit of electricity, all of a sudden you can jump way up there. If you can turn on a light and have light, if you can flip a switch and have light, if you can turn on a knob and have heat to cook your food, and you don't have to burn animal waste inside your home, your quality of life increases dramatically. And this is a statistic that I just learned recently that breaks my heart. This story that I just popped up here, this headline of collecting water, often colossal waste of time for women and girls. If you read the first line of this, every day, that means today, 200 million hours of women and girls' time is spent carrying water. 200 million hours. Think about how many people, how many lives are spending huge parts of their lives carrying water. You want to drink, you wash your clothes, you want to do anything, you have to walk down to some water source, fill a bucket, and walk back home with it. And that's not clean water, that's just water. And then tomorrow, guess what? 200 million hours, women and girls' time carrying water. If we had just a little bit of clean energy, a little bit of electricity, and we could pump that water and purify that water, how would we bless people's lives? How would we change their life? Could those mothers teach their children to read? Would that open the horizon of what their world looks like? A little bit of electricity, a little bit of energy changes people's lives. The third critical need is just water. We talked about the water and the 200 million hours of carrying that water, but then we say clean water. There's a billions of people that do not have access to clean water. And then when we say, well, what about water to clean things with, or irrigation, other things, then it increases to billions of people. 1 in 3 people need it. So these are the critical needs of the world that we're trying to address in this project. Do we have energy to bring people out of poverty and raise their standard of living? Do we have medical isotopes to treat cancer? Do we have high process heat to desalinate water and do things like that? And there's lots and lots of studies that says this is what the world needs. But this quote from the United Nations says, nuclear energy is indispensable for eliminating poverty, ending hunger, providing clean water. And so that's what we're doing. And the technology we're using is molten salt reactors. So let me tell you a little bit about that. But first, the mission of ASU Next Lab is to directly hit these issues. The mission of ASU's Next Lab is to provide global solutions to the world's need for energy, water, and medical isotopes by advancing technology of molten salt reactors while educating future leaders in nuclear science and engineering. That's what we're looking for, is really to bless the world. Molten salt reactors, they're safe, they're clean, they're efficient, they're multifunctional, scalable, carbon-free, reliable. They can use a wide range of nuclear fuels, including spent nuclear fuel. We'll learn more about these as we go along. But let me just tell you about the 2 things that are different. So if you're familiar with current nuclear power, that's awesome. If you're not, don't worry about it. There's just 2 things that are really different about old technology. I'm talking about reactors that we've been using for the last 50 or 70 years in this nation, and what we're building at Abilene Christian University, this advanced reactor type called a molten salt reactor. We're using a molten salt as a coolant. So in this little picture here on the left, you see our Morton table salt. We're all familiar with that. This is, if you're a chemist, this is sodium chloride, right? That's the chemical makeup of this salt. And you see the white form of it when you pour it out or shake it out. That little blob in the middle is what happens if you raise the temperature of the table salt. When you get over about 850 degrees centigrade, it actually becomes a liquid. And then if you let it cool back down, you have like wax forming in a mold. And so what you have there is, this was sodium chloride that we raised up to about 1,000 degrees centigrade, and we allowed to freeze in a bowl, and then we turned the bowl over and dumped it out. And on the right, you see a liquid. It looks like water or oil or something, but that's actually a salt. It's a solid at room temperature, but when you raise the temperature, it melts and it's a liquid. So molten salt is just salt in a liquid form. So why do we want to use salt, molten salt as our coolant? Well, it allows us to operate at high temperature and low pressure. And so water is a great coolant, heat transfer fluid or coolant. We use it in our cars, for example. Our antifreeze is mostly water that takes the heat generated in our engine and takes it to our radiator. But the problem is when you get it up to like 212 degrees Fahrenheit or 100 degrees centigrade, water wants to flash to steam. So that means our water wants to become a vapor, high pressure, and it's that high pressure that is dangerous. And so reactors only operate up to about 300 degrees centigrade, and it really doesn't matter if it's a nuclear reactor or natural gas powered or coal or oil or concentrated solar. If you're using water as your heat transfer fluid, you can't get above about 300 degrees, which means you don't get as much electricity for each unit of thermal energy. The graph on the right just says we're more efficient at turning thermal energy into electricity the higher temperatures we operate at. And then the low pressure just means it's safer. When you have a high pressure thing, when you have a leak, it spews. And high pressure is dangerous. And so if we're able to operate at low pressure, that means it's safer, it's walk away safe. And then finally, if we use molten salt or coolant, it enables our second key requirement, which is liquid fuel. So old nuclear technology uses solid fuel rods. You've probably heard of fuel rods. You take your uranium and you put it in a ceramic form, and then you surround it by a piece of metal called metal cladding, and you put it in a fuel rod. And so you have your radioactive material encapsulated inside of a metal cladding. And that's wonderful if you want to keep the radiation away from people, which we want to do. But the problem with this is not all things that are radioactive are bad. Remember those medical isotopes? We want to get our hands on those things and give them to doctors to save lives. And the other problem with this is that with this old-fashioned fuel rod is you only use about 5% of the energy content there, and you throw away 95% of the energy. So it's like pumping your gas, your car full of gas, pump 20 gallons of gas in your car, using 1 gallon, and then throwing away the 19 and calling it bad waste, toxic waste, right? It just would be a dumb thing to do. But that's what we're doing because this technology of solid fuel rods only allows us to use about 5% of the energy content before we have to throw away the fuel rod because it becomes unstable and we can't do it. So we increase waste and we don't have very good utilization of our fuel and we can't get our hands on the isotopes. So go into liquid fuel, and liquid fuel, all I'm saying here is it's like dissolving sugar in a cup of coffee. We take our uranium fuel and we put it inside the molten salt and it dissolves and it distributes throughout the coolant. And so that's our second real advantage. And those are really the only two changes from current nuclear power to these advanced reactors. Molten salt cooled, liquid fueled. So a little history. We started this project back in 2015, 16. By 2017, we had a small group of people working on building a salt loop in our labs here at ACU. In 2018, we grew and built collaborations with Idaho National Lab, and then we built our molten salt test loop. So what's shown in this cartoon, well, in this picture here, is this little square thing at the bottom. Think of that as an industrial-sized crock pot. That's where we put our salt, and that raises the temperature up to 1,000 degrees if we want. And then there's a motor above it and a shaft to an impeller that takes the salt and pumps it around this loop. So this metal pipe here is a loop that allows our salt to flow through. But remember, at room temperature, the salt, it becomes a solid. So we have to put heaters around the pipe and then insulation around the pipe. So when we're using it, it looks like the image on the right here. So the image on the right is our molten salt test loop. The image on the left is a thermal image of that, which the bright spots are high temperatures and the dark spots are cool temperatures. So you see the little plot on the little graph on the right, 82 degrees shows the things that are like white. That's the temperature in degrees centigrade. And the dark blue is also the cooler temperatures. And I wanted to point that out so you'd understand this next video. So with that loop, we put in a valve so that when we heated the salt and we turned it on, we could open a valve and we could see the molten salt flow out. And for me, this was the first time I saw molten salt flow in our labs because normally it's behind the pipe. But let me turn on this video and start it. And the left is what you see in the lab. And the right, you see the temperatures in degrees centigrade. So on the left, it looks like water coming out. It doesn't look very fancy. But if you look to the right, it's 195 degrees centigrade. And at that temperature, it can't be water. It'd be flashing to steam. And so what happens if we have a leak in our reactor that's cooled by molten salt? Well, this demonstrates what happens when salt leaks out. It doesn't flash to steam. It doesn't rise in the atmosphere. It's a liquid that falls to the ground. If you have a catch pan, it hits that catch pan, spreads out, and starts to freeze. And you'll see that last drop doesn't actually drip on there because it froze on the can. And so if it's a small leak, it might self-heal itself. But what you have is you have the salt in your catch pan, and you see these little black dots in there. Those are impurities. And so if you imagine that being the fuel in salt, the radioactive material, no radioactive material goes in the atmosphere and starts drifting around the world if there's an accident. If there's a leak in our system, it falls down to a catch pan, it freezes, and it self-encapsulates any radioactive material. So it makes it sort of what we call walk away safe or inherently safe. So let me not watch it again. In 2018, the Department of Energy, the United States Department of Energy came to ACU. The Principal Deputy Assistant Secretary for Nuclear Energy came. This is what they call NE1. The chief official for nuclear energy in the United States came here, saw our little loop, saw our vision, and said, hey, I love your vision of blessing the world, tackling its critical needs. And I love the fact that you're building things in the lab and having students work on them with their hands-on experience. I want you to come to DC and tell me how you're going from this loop to blessing the world. So in January 2019, President Schubert, the president of ACU, the man on the right, along with Doug Robinson, who was the primary funder of the project, in the middle, and then myself, we went to DC and we said, we want to build a molten salt research reactor at ACU. We would like to use the same program that every other university does to get fuel from the Department of Energy, and we need some help. And we need some help working with the Nuclear Regulatory Commission, which is the people that license it. And they said yes. They asked us, how long is this going to take? And we said, we think this is a 5-year project. They said, when does it start? We said, when you give us in writing that you'll give us fuel. And it took them almost a year, but we got this letter of support that says they appreciate what we're doing. They want to support us and they'll do it. And so at that point, Doug Robinson, the man that was primarily funding this, stood up Natura Resources, a for-profit company whose goal it is to take this technology and deploy it to the world, because it does us no good to have a really cool research program at ACU if we can't deploy this to the world. And so Natura Resources committed to answering the world's needs for reliable energy, medical isotopes, clean water by developing commercially deployable molten salt reactors. Again, sounds a lot like the mission of Next Lab, except it's that last step of how do we get this out into the world. And so we're partnering with, and there's no surprise there, we stood up and worked together to get to this point. So Natura Resources stood up a research alliance. So ACU is partnering with the University of Texas, Texas A&M, and Georgia Institute of Technology. All together, we're known as the Natura Resources Research Alliance. And this is some of the principal investigators from all 4 of those institutions working together. And so what we're trying to do is build a molten salt research reactor. And it's very, very similar to a reactor that was built at Oak Ridge National Laboratory in the 1960s. So for 4 years, the molten salt reactor experiment operated at Oak Ridge. So these pictures here are pictures that are literally over 50 years old of a reactor that would use this technology. So what I'm talking to you about is not, does it work, or we're not sure if it works, or it works in theory. This is something that was done before I was born. And so it's done a long time ago. And so you can ask, why are we not using that? And if we were in person, that's how I always check to see if you're actually listening to me. If someone asks that question, why are we not using it? Well, it doesn't do a good job of producing bomb material. And back at this time, that people weren't worried about nuclear waste, and people weren't worried about a lot of things. Is it more efficient and things like that? Today, we care about those things. The customer for the technology in the 1960s was the Department of Defense. We need this technology to power our submarines. And they wanted it fast. And for a submarine, a water-cooled reactor is not necessarily a bad thing. Today, to address the energy needs, the medical isotope production, the process heat to desalinate water that we need this technology. So we're building the research reactor. We share a lot of concepts that are the same. We're using a lot of the same salts, fuels, moderator, a lot of things. We're simplifying it in a lot of places where we can. We're not using high enriched uranium. We're dropping power down order of magnitude. We've made it simpler so that it's safer. This is a cartoon picture of our molten salt research reactor. The picture on the right, the outer edge is a reactor enclosure. And if you go in beyond that, there's basically what we call our reactor thermal management system, a fancy name for an oven. It's an insulated box with heaters inside, which you need to have our salt loop inside of that. And so the big box in the center, that's the core. The salt comes in the bottom cool. It gets heated up due to the fission process. It goes out the top through a pump, through a heat exchanger where it loses some thermal energy, and it comes back in the bottom at a lower temperature, and it just keeps circulating through there. It's a simple circle, but at the bottom of all that, you'll see this sort of this container that has a round bottom and a flat top, that's our drain tank. And if we equalize the pressure at the top and the bottom, then gravity will allow all the salt to drop and the fuel. So we literally pull the fuel out of the core, so it's impossible for the reactor to go critical. And then it passively cools off, just like our picture had, and it's passive shutdown. This is the size of this reactor enclosure. So there's a person, you see it's like 20 feet tall and about 10 feet diameter cylinder. This is the group of students at Abilene Christian University working on the project. And so this is a group, we normally have somewhere between 50 and 60 students joining about 20 to 30 faculty and staff on the ACU campus. And this is, in the summer, we work full time on it. During the school year, the students go to school full time and work with us part time. We have lots of different projects, and I won't go through them all, but on the left-hand column is a small salt loop, the way you saw earlier, and then a higher temperature and a bigger salt system, and then the chemistry that's necessary to support it. So there's isotope extraction. How do we get those medical isotopes out to give them to doctors? The next column is instrumentation, data acquisition, filters, component test stands, and all of this is leading to the bottom right, the molten salt research reactor. So we have lots of hands-on research projects. We have a bunch of patents we're collecting and papers we're publishing, but we're making news. In 2020, the Nuclear News, it's a publication by the American Nuclear Society, said, hey, 4 universities working together to build a molten salt research reactor. We made news of that. And we were the first university that said, we want an advanced reactor. And then the next year, the University of Illinois says, hey, we want an advanced reactor also. And then in 2022, we had Purdue and Penn State and McMaster up in Canada all said, hey, we want reactors also. But that's fine. We're glad for them to want it. We think that validates our point. But we've gone ahead and we've submitted a construction permit to the NRC, the Nuclear Regulatory Commission, to build our reactor. And we've actually built the building to house it with our that's shown in the picture there. And that building is the Science Engineering Research Center. So it's a 28,000 square foot facility. It was designed a couple years ago. It was completed last year. And in September, we moved into the building. So for the last 6 months, I've been officing in this building. This is what it looked like when it was brand new. Since then, we've added some grass and trees around it. So it looks more like a nice building. But you'll see that there's a few glass windows in the front. That's where our office is. But really, the big part of the building is that big square in the back. And that big square, if you do a cross section of that building, what you see, the fancy thing about that high bay is it has this trench inside of it. And that hole that you see the little guy in the bottom of for scale size, that's a hole that's 25 feet deep, 80 feet long, and 15 feet across. And what that does is that allows us to build our reactor, drop it in this hole, put a concrete lid on top of it, and deploy it. And so when we deploy the reactor, it looks something like this. That little thing in the middle inside is surrounded by a bunch of concrete inside this building. A cross section and cut it the other direction. It looks like this, that 80-foot long trench. The reactor is on the left-hand end. We have some support systems and then room for a future reactor or a future project on the right. This is a cartoon picture of a life-size 2-dimensional reactor. And what we've shown here in this little image is we would deploy it, we'd build it off-site, it would ship here on a flatbed truck, come through that door in the back, and then our 40-ton crane would just lower it down into this trench where we then would put a concrete lid on top of it and be ready to operate. And so this demonstrates sort of what we refer to as small modular reactors. All right, I appreciate you're listening to this. So where are we? This Natura Resources Research Alliance is leading the way in molten salt reactor development and deployment. ACU is licensing the first advanced university research reactor with the Nuclear Regulatory Commission. The Nuclear Regulatory Commission is the entity in this nation that gives you permission to build and to turn one of these things on. And we have submitted a year and a half ago our application, and we're under review, and they've told us to expect that approval this summer. There's 2 things they approved: the environmental impact and the safety review. The environmental impact was just last week finalized and finished, and it found that there was no measurable effect. So building this reactor would not give us a measurable effect on the environment, and so it is safe to build on a college campus. In fact, ACU has built our newest dorm literally across the street from this reactor facility, and so we're very pleased that they've confirmed what we've been saying. ACU has completed this this building, our Science and Research Center, to house the molten salt research reactor. And we're on path to be the first operating advanced reactor in the nation. So we're pretty excited about what's happening here in the state of Texas at Abilene Christian University. And we're working closely with our partners, and it's an exciting project. So I'll thank you. These are a bunch of people that, Nature Resources is really powering this. We have gotten support from all these other entities, and there's a website you can go to and find out more about it. So I've been talking way too long. I'm ready for some questions.
Awesome. Thank you so much. Yes, I realized I had the chat not activated, so I just fixed that, students. So I apologize on the questions if you had them throughout the presentation. The chat is working and the Q&A feature is up and running. So that's on me. I'll take responsibility to why you didn't get any questions throughout your presentation. But I feel really good about being an ACU alum at this point in my life. So.
Can I go ahead and kick off questions real fast? So one of the things you helped found and start the very first of its time, but it sounds like there's lots of interest from other universities to do something similar. Clearly there's been some really seemingly interesting collaboration. Is this the kind of thing that it makes sense to have lots of universities popping up here, there, and ever? Or does it make, I say it because you think about, maybe it's not the same, but with cancer research, you have a lot of places that collaborate and a lot of places that do their work maybe more in silos. Like, what makes sense? And kind of what is the future of kind of the development of this type of technology?
That's a great question. So when the nuclear fission process was first discovered, it was an amazing time in development from the time we discovered and let me stop and geek out just for a second. I think there's some science people on here. So let me just say that the exciting thing about nuclear power is, there's only 4 fundamental forces in the universe, right? And the electromagnetic force is basically the chemical process. So when you take gas and you burn it to produce energy or your oil or something like that, that's a chemical process. Electromagnetic process is like if you have hydrogen and oxygen and you want to combine them in H2O, that burns and releases thermal energy. You can think of like Hindenburg, for example, right? But that's a chemical process. The other force that we're all familiar with is gravity. And so gravity is a great force for like when you have a dam and you have water at a high elevation behind it and you want to allow it to run downhill, turn a turbine and release it, we have that energy that can be produced from gravity. But the other 2 forces we don't encounter much in our everyday life, and that's the strong and weak nuclear force. That's the force that keeps the nucleus together, and we don't deal with it much, and that's generally a good thing because it's such a strong force that when you play around with it, you release a lot of energy. And when I say a lot of energy, I mean 1,000,000 times more energy. So when you rearrange the electrons with electromagnetic force, or you allow something to roll downhill, the amount of energy you get if you go in and you rearrange the nucleus is 1,000,000 times more. And so I think of Spider-Man, right? With great power comes great responsibility, right? If you're going to play with the nucleus, you need to be careful. But when man learned that you could rearrange the nucleus and release energy, from that time until they said, oh, this is a great energy source, let's build a reactor, was like a decade. From discovering it existed to actually building the first one. And so very rapidly it happened. And in those early days, every university built one of these things. So if you go back to the 40s, 50s, 60s, every university had their own research reactor. And so there was 100 of them around the nation. And if you look at what's happened over time, as a nation, we quit building them in the 60s, 70s. And then we've just been slowly decommissioning them. And so currently we have a fleet of research and test reactors of under 30 in the nation. This is a time where we're saying we really need clean energy. We really would like to get our hands on medical isotopes. So as the number of students interested in nuclear engineering and clean power is on the rise, and the world is saying we need more clean nuclear energy, we have very few research reactors to support them. And so this will be the first new research reactor in over 30 years in this nation. And so do we need more than one? Yes. And the other thing is that of those, 25 or 30 research reactors, they're all very, very similar. They're water-cooled, solid-fueled reactors. And so the different reactors are being talked about. The University of Illinois is talking about having a high temperature gas cooled reactor. So not using salt as the coolant, but just air as the coolant. And there's pluses and minuses to the different technologies. But I think there needs to be a lot of new research reactors, different technologies. And so more people can get their hands on them and more experience. And we can really have sort of a resurgence of clean, reliable, safe energy. Sorry, you got me going on 3 tangents there. I'll be more pointed in my next answer, I promise.
What was it that I'm going to bring it to you a little bit. What was it that led you to how did you discover kind of your passion and the engineering and physics, and what was it that kind of it made you pursue that?
That's a great question. So I had a great teacher in high school. I guess I've always been curious how things work and how, the why behind it. And I love to take apart things and see how they worked. And in high school, I was blessed to have a teacher that really was, inspiring and loved to encourage people to ask questions and try things. And so I was able to really lean into it. And I remember the opportunity to go to actually a Texas Energy Science Symposium. And so this was a long time ago, and people were saying, where are we getting our future of energy? We've always known that hydrocarbons were limited, right? There's, no matter how much oil we find or coal we find, at some point they're going to run out. We're using them faster, we're making them. So there has to be something after that. And so what is that going to be? And so at the time, I remember being exposed to fission and fusion and the power and the nuclear force and the opportunity there. And that really, truly is virtually a limitless type of supply. It's what powers the sun and stars, right? So you're talking about billions of years of supply. And so that was exciting to me. And I literally remember talking to my science teacher and saying, hey, if I really want to think about nuclear power, is that chemistry? Is that physics? Because high school, I loved the chemistry, right? I loved things burning and blowing up and changing colors and all the fun there. He said, well, that's physics. And so that sort of said, okay, I need to do physics. And I love that was really the fundamental whys, right? Why does this work? How does that work? How does the universe work? That's really what's there. And engineering is satisfying and interesting, but engineering sometimes solves the problem, but doesn't really worry about the why, right? Engineer, and they do extremely useful things. And one of the things I love about this project is it's so interdisciplinary. We have chemists and physicists and engineers, and within engineering, we have mechanical engineers and civil engineers and electrical engineers and chemical engineers. They're all working together on the project. So I love the interdisciplinary nature of this.
Awesome, thank you. Okay, we've had some students come in, so I'm gonna bring you guys over, ask you to unmute, ask your question, and then I'll send you back. Ashwin, I'm gonna bring you over if you have the ability to unmute.
Can you hear me?
Yes.
Okay, so I was gonna ask, sorry if you've already covered this. What is the timeline to actually start implementing and utilizing this technology worldwide? Because you were talking in the beginning of your presentation about how important it is and the really big negative impacts on the lack of energy in these less developed countries.
No, it's a great question, and I apologize. I did not cover that, so thank you for asking. So I'll tell you, before I answer it, I'll say, if you're familiar with nuclear, then you'll be shocked at how fast I'm going. If you're familiar with how fast industry likes to work, you're going to be shocked at how slow this goes. And so it sort of depends on your point of view. But we said we wanted to go from 5 years from a standing start to a research reactor operating. We're probably going to end up being closer to 6 years. And what I'll say is that we've been for almost the last 2 years waiting on the federal government to agree that what we want to build is safe. And so they've been reviewing for over 20 months our construction permit that is asking them, do we have permission to build this device? And we're hoping we're nearing the end of that. And then we have to go and say, do we have permission to turn it on and operate it? And we expect them, again, maybe another 2 years. So the 6 years of doing this, 4 years is just waiting on the federal government to say, yes, it's safe and you may do this. And going back to in the heyday of reactor development, there's national labs. Idaho National Lab built like 50 reactors and turned them on, tried them, learned from them, and turned them off in literally like 15 years. So they're building like 3 or 4 a year, and turning them on and trying them and stuff. And and so why were they so able to do it so quickly then, and we're slower now? So if in 2026 we can turn on this reactor, Natura Resources is very aggressively hoping that by 2030 they can deploy their first commercial. And then after that, we'd like to build these things basically on an assembly line and start turning them out, not one in a decade or something like that, but every week we'd love to have one of these deployed. And does that meet the world's needs? No, not even anywhere close. The world has huge energy needs. And so we need to scale up even beyond more than one of these reactors a week. And so we talk a lot about the gigafactory idea. Let's build a huge factory that just produces these, and we produce 3 a day, and we can deploy them around the world. And if we want to meet a lot of the needs that the world has, that's sort of what we're looking for. Great questions.
Thank you. Okay, Evan, I'm going to bring you over, ask you to unmute, and then you can ask your question.
Hello.
Hi.
Yeah. Okay. How's the amount of energy of your nuclear reactor compared to other kinds of fuel like gasoline?
So, if you say how much energy can I get out of a gallon of gasoline, or if I had the same mass, right, of uranium, I get 1 million times more out of the nuclear process of rearranging it. So instead of one, train load full of coal, I need 1 million train loads of coal to get the same thing out, that same value of uranium. So that factor of 1 million is just really hard to get your head around. Our reactor is going to produce, if your question is how fast are we going to release energy, then the answer there is it's going to be 1 megawatt. And so that's an energy release rate. So how much energy will we produce every second? We'll produce 1 million joules a second, is what we'll produce. Now, commercial reactors are 1,000 times bigger than that. So we're really small as far as nuclear reactors go, but this technology scales up. And so we're easy to make big ones if we wanted to, or small ones. People talk about micro reactors that are basically the size of this research reactor that you could take to remote locations where they need reliable energy, but they don't have a source. Great question.
All right, we've had a bunch come in, so I'm just going to keep bringing them over. So Sashank, I'm going to bring you over. If you could unmute yourself and ask your question.
Is there a difference in the amount of energy produced by molten salt reactors compared to regular nuclear reactors?
So we're building a reactor that's really, really small. The definition of a research reactor by the Nuclear Regulatory Commission says for this type of reactor, we can't make it bigger than 1 megawatt. So that's how fast we release energy. This technology is scalable. So we could build it smaller, we could build it bigger. The reason commercial reactors are so big, the light water cooled, solid fueled reactors, are that they need to have this huge containment dome, because if there's ever a leak there and the water flashes to steam, you want to contain that. And so that huge containment dome is so expensive, the economy of scale says build it big. And so that's why the most recent reactors, the Vogtle reactors that came in Georgia, they're gigawatt size, 1,000 times bigger than this research reactor. What Natura is talking about is building a reactor that's like 200 times bigger than this reactor. It still fit on a flatbed to be able to deploy it and produce something like 200, 250 megawatts of thermal energy.
Okay, Joe Bartlett, I'm going to bring you over.
Can you hear me?
Guys.
Yes.
Oh, okay. So I understand that in the 50s and 60s, the molten salt reactors weren't used because of the need for like maximum energy output. But why hasn't the method been considered like whenever the need for cleaner energy was created?
Yeah, it's a great question, and like I said, that's sort of the are you paying attention to what I'm saying, right? Because if people demonstrated this in the 60s, why on earth have we been letting it sit on the shelf, collect dust for so many decades? And the answer there is, who was the customer? The customer in the 60s was the military, and water cooled was a pretty decent solution for a submarine where you're surrounded by water. Now, when you want to translate that to on land for commercial use, it's not really a good choice. There's a lot of drawbacks, but the heavy lift of developing the technology was already there. And so it was relatively simple. And then you had a regulatory environment that came in, the Nuclear Regulatory Commission came in and said, let's not allow innovation. Let's just keep adding on more and more and more regulation onto the current technology. And so, you think about our cars, or what about your phone? What did a phone look like 50 years ago? All of our nuclear power, right? That's producing virtually 20% of the clean energy in this country is nuclear power. That's all based on 50-year-old technology. It's crazy because the regulatory said you can't change anything. If you want to change something, you have to prove it to us 12 times over 20 years that it's safe before we can do it. So you have reactors that are still doing things the way they were done 50 years ago. And that's just crazy. And so we have to look at it and say, if we don't build more safe, clean power, what happens? And for me, the trigger came off, and 2 years ago, Winter Storm Uri came through Texas, and we had that week where we had millions of people in the state of Texas without power, and we had hundreds of people die in the state. Why? Because we didn't have reliable power, right? We have power that depend upon the sun shining, solar, the wind blowing, windmills. Those are fine sources of energy for the right application. If I want to power my calculator, I use solar powered. If I lose the sun, no one dies, right? But when we depend upon the electricity to provide heat to my home, to provide water, especially for elderly or hospitals, and we lose that power, people die. And so we need reliable energy. And so that's why we must get away from this slow process, and we have to get to advanced nuclear. So sorry, you hit me and I started going. I think I answered your question there.
I love the passion. Like, you can definitely tell that it's there and that you are in the right space. So that's awesome. Okay. Okay, Joseph, I'm going to bring you over, ask you to unmute.
Hello.
Hello.
I think you may have covered this as well, but what are the side effects of this reactor, and what is the consequence if the reactor malfunctions that results in like other issues that are associated with nuclear reactors, such as the Chernobyl issue?
Hey, great question, right? This is the the elephant in the room. If you can't build something safe, then let's not have it, right? And so there's a couple things I'll say. Is one is the report that was just finished last week, and it's a public report. You can go to the Nuclear Regulatory Commission's document server and look for the environmental report on Abilene Christian University, and you can read how it says the impact is small. And what's their definition of small? It's undetectable, right? And so the environmental impact is going to be zero. And a scientist can never say zero because it's just how well can you measure it, right? And so their statement was it's going to be unmeasurable effect on the environment. Now, if there's an accident, and again, Chernobyl is happy to talk through all the accidents, right? There's 3 Mile Island, then Chernobyl, then Fukushima. Chernobyl is a design reactor that was designed to produce both bomb grade material and electricity in the same exact facility. And so they had to sacrifice safety, and then they allowed people that weren't trained with it to come in and make decisions about running tests on it, and they operated it very poorly. And if you watch the short story Chernobyl, you saw a lot of it in there, right? You had they wanted to run a simple engineering experiment. Can I use the kinetic energy from the turbines to power the pumps in a backup situation? They planned to run that experiment in the middle of the day, but because of poor operation of the reactor, they almost shut down the reactor. So they pulled the control rods all the way out. The automated system said it's an unsafe state. You need to shut down the reactor. And 2 minutes later at 2 a.m., they started this test. It was a stupid design, stupid operated in an unsafe environment, and they paid the price for that. I would never promote using unsafe designs. I'm thankful we have a regulatory commission that wants to make it safe. We need to make sure that it continues to be safe. And so with this design, if there's ever a leak, pipes leak, things happen. When it happens, what happens? Salt pours out into a catch pan. There's no flash to steam. There's no rise into a plume of smoke that drifts around the world, but it falls to a pan, it cools off, and it becomes a solid. So we say, well, you have a mess? Yeah, but you have a mess right there. right? It's not in the atmosphere drifting around. You have a mess right there in your catch pan, which you can clean up and put back together without ever leaving the containment around it. And so nuclear power can be done safely. It has been done safe in the Western countries for decades and decades and decades. The only nuclear accident that ever led to deaths is the Chernobyl, right? 3 Mile Island, Fukushima, 0 deaths from radiation from those environments. A great question. Thank you for allowing me to talk about it.
All right, which Carter? We have 3. Okay. Okay, Carter, I'm going to bring you over.
Oh, can you guys hear me?
Yes.
Just salt's known to be naturally corrosive, and I know you said you had the drip pan as like a contingency for when things go wrong, not wrong, but like when that happens, not if. If it like, because you said it solidifies because it's meant to be cooler down there, like eventually, like what if that like builds up or like just starts corroding and affecting its neighboring materials because it's just naturally corrosive towards like steel, aluminum, and a bunch of other metals.
Absolutely right. A lot of people refer to this as a chemistry reactor, and partly that's for this point is you need to be careful of it. Corrosion is a chemical process. What I'll tell you is that for corrosion to be present, you really need 3 things, right? You need the high temperature, you need the salt, and you need the oxygen. So if we have high temperature salt but 0 oxygen there, then you don't get that iron oxide, that rust, right? It doesn't drive the corrosion. And so what we do with our salt is we very, very carefully process it and get all the oxygen out. And then we put it in and we have a very tightly sealed system that doesn't allow the oxygen in. But we also are monitoring that. And if we ever see it start to change, we take steps to treat the redox potential of the salt. If you're familiar with the chemistry there, we keep the redox potential in the right range, which basically means keep the oxygen out, or you put in something else that wants to grab the oxygen more than the metal around it. Corrosion will be an issue. There will be a limited life for these reactors. These reactors probably won't operate for 50 years. These reactors probably only operate for 20 or 30 years before the metal becomes questionable, and we say, let's take the salt and the fuel and put it in a new reactor and decommission that. So absolutely, corrosion is a concern of ours. We have a lot of tests happening at ACU to study the corrosion in different situations and monitor it and understand it. Corrosion is a big issue, but it's controllable, it's fixable.
I think this question that came in from Zachary, you kind of mentioned part of it just then, but I wanted to make sure that it did get asked. He doesn't have a microphone, so I'm going to ask it for him. It's a 2-part that kind of go together. How did you find out about your safety measures were adequate, which you kind of spoke on? But in doing it, was it trial and error, or was it more like you figured it out doing like the math behind what it could be?
Great question. And we used all of these tools, right? And so depending upon exactly which question and what we're doing, if we're saying, what do we have to do to make sure we shut down the fission chain reaction? We can, of course, use math for that, but then we will double check it with this reactor when we have a small little reactor before we build a big one. And part of guaranteeing that we can build this little reactor is the fact that we know what's the worst case scenario that could happen when you have a small source term, when you start with a small fuel loading, et cetera. There's other places where we do things. So, you saw us intentionally allow salt to fall out into a catch pan so we could study that. There's much more sophisticated tests that we do for real. So in some real sense, this whole effort, this research reactor is the experiment. And when it's successful, we understand it better, the corrosion and the safety features and the yada, 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 then we'll scale it up and we'll deploy it commercially. But we're building a very small, safe thing first because that lets us confirm experimentally what we have modeled mathematically. So we use both those tools.
So your students that you're working with right now, they are in their undergrad, correct?
So I
Mostly,
showed you a picture of the 60-ish students at ACU that are working with us. Those are all undergrad students. At the other universities, they have graduate programs in nuclear engineering, and so there's a variety of graduate students and postdocs at University of Texas, Texas A&M, and Georgia Tech that are working with us. But at ACU, we have undergrad students, and so we give them the opportunity to jump in and work with us. And so they get the chance to come in and put their hands on the equipment, help design the equipment, do some of the mathematical calculations before we build it, and they're part of the whole process beginning to end. Our students are engaged with us.
that's an awesome opportunity. Okay, looks like we had one more student from one more question from a student, and then we'll end with our final question and then wrap up around our 7:30 mark.
So I was wondering if the molten salt reactor was the first major innovation in changing reactor technology.
That's a great question. And I'm a little biased because it's what I believe is the best technology to move forward on. As I told you, University of Illinois is using a gas-cooled reactor design, and there's other people that want to use different forms of coolants or different moderators or different fuel forms. And so there's a lot of ideas out there, and it's very interesting. I encourage you to look into it. I believe that in terms of being inherently safe, being inherently efficient with the amount of fuel you use, to minimize the waste you produce, give you access to the medical isotopes. For all those reasons, I believe that the molten salt cooled liquid fuel is really the most advanced technology.
Okay, we did have one more. Oh, go ahead. Were you going to say something else?
I was going to answer
Okay.
real quick. Go ahead. I'm happy for you to jump in and answer.
So you can just if you saw the question, go for it for time's sake.
Okay. So to control redox potential, we'll actually put beryllium in our salt. We're going to use a lithium fluoride, beryllium fluoride salt for our reactor. And if you add beryllium, then it helps us reduce the redox potential. And so we'll just add beryllium to the beryllium fluoride salt mixture that's there already. What do you think the next step in energy will be? Oh, I think it's going to be this molten salt reactor we have at ACU, and then they're going to start mass producing them, and we're going to have molten salt reactors deployed all over. What else would it be?
Oh, well,
will it take the same level each time for the approval? Because I mean, you said it's about 6-year ramp up process. Every single time someone applies for this, is this what's maybe keeping some of the private dollars to do this on their own?
This is a huge hurdle for private dollars. Imagine, please invest in my company, and I want to spend the next 6 years building a test that's not going to produce any revenue, so I can spend another 6 years to build something that will produce a revenue. It's hard to get someone to invest dollars that are that far out. And so that's why it's really that and the regulatory environment are tough things to get over. So we've started with a small one at a university to try to minimize that. But if we get this construction permit later this year, this will be the first time the Nuclear Regulatory Commission has ever licensed a liquid fueled molten salt cooled reactor or anything other than water cooled and solid fueled. It'll be the first time they've licensed that. And so that's going to be a big deal. That's going to be a huge deal. And I think that gives some confidence to investors that there is a path forward to deploying this.
All right. So I think we hit all of the student questions.
The next step after this reactor will be build a bigger one commercial, Zach. We want to build this research reactor, and we learn from that, and then we say, okay, we understand its safety and how to control corrosion, et cetera. Let's build one 200 times bigger that we can actually start harvesting energy from it.
Look up done in Abilene?
Oh, I don't know where
that like where ACU is, or would that be somebody else would take that on?
So Nature Resources would be the company that does it, and they'll probably partner with someone. And yeah, universities need a lot of energy, so could ACU want it? It's possible. But I know Nature is talking to a lot of people because everybody wants reliable, clean, safe energy. And so whether you want to put electricity on the grid or power a data center or refine chemical processes, all those people want to have energy that's reliable, clean, and affordable.
Okay, well, we are coming up at our 7:30 mark, and I want to make sure to respect that for you, but also students. I think kids were taking SATs and things today, so I know you guys have a lot on your plate. So in the chat, can you help me thank Dr. Towell for joining us this evening? I know that this is we hear kids talk about this, and we hear kids doing science fair projects around some of that same language. And so I know this was exciting for those that were able to join. So we really appreciate you taking time to say yes and spend this hour with us and give us a look into what you guys are doing at ACU. And this can just be our plug for those to apply at ACU, become a Wildcat. It's a great area, good food around. So thank you so much.
You're certainly welcome.
So
I appreciate that.